Welcome back. We're going to continue today, and we will pick up where we left off with our study of the balance of energy. In particular, we will focus upon one of the terms that came up during that study, which is this idea that the stress does work at some rate, which translates to a power, by deforming the body, right? So here's the picture. Well, it's not a picture. Here is our 3D setup, right? So we have the body in its current configuration, and it's deforming. And we know that as it deforms, there's a stress tensor defined at every point in the body. Furthermore, the body is deforming, and we have many measures for this deformation. We have this notion of stretch tensors, and we saw a number of them. We also have a strain tensor, as well as a rate of deformation tensor. And we saw that the stress does work by acting on this rate of deformation tensor. It does work at a certain rate, right, which is power. So we're going to pick up with this idea, and the title of this segment will be Work Conjugate Forms. Okay, and let's recall from our study of the balance of energy. So we introduced this term that I believe we referred to as the internal stress power, right? I don't recall that we actually introduced this particular notation for it, but we'll do so now, okay? And what we showed was that this is the integral over the current configuration of the Cauchy stress contracted with the rate of deformation tensor, okay? And this is what we call the internal stress power. Okay. Now, around this development, we also, or actually a little following this development, we also introduced this notion of alternate measures of stress, right? So we also, introduced alternate measures of stress. And those were related to the Cauchy stress in the following fashion, right? We saw that P, the first Piola-Kirchhoff stress, it is J sigma F inverse transpose, okay? This is the first Piola-Kirchhoff stress. Okay, we introduced tau, right, which is J sigma. This is the Kirchhoff stress. And we introduced S, which is J F inverse sigma F inverse transpose, and this is what we call the second Piola-Kirchhoff. Okay, what I'm going to attempt to do now is to demonstrate that this expression for the internal stress power can also be expressed in terms of these other stress measures. And of course, what we should expect is that if we rewrite this expression that we have on top here, if we rewrite this in terms of other measures of stress besides the Cauchy stress, we should see that there are different ways of writing out the rate of deformation, right? Okay. And this sort of combination between a particular stress and a particular rate of deformation is what we mean by conjugacy in terms of work, right? Because remember, what we've written out here as an internal stress power is really a rate of work, right? Okay, so let's see how this works out. Okay, let's start then with what we have. Integral over omega t of sigma contracted with d little v. The very first step that we can take is to observe that we can just rewrite this as an integral over omega naught, okay, by recognizing that while we may hold the integrand the same, d little v is basically the determinant of the deformation gradient times d capital V, right, where d capital V is the elemental volume in the reference configuration. But then when we multiply sigma by j, we get back the Kirchhoff stress. Okay? So that's the first of our alternate work conjugate forms. And here, note that nothing needed to be done as far as the rate of deformation tensor was concerned. We just scaled the Cauchy stress by the determinant of the deformation gradient to get the Kirchhoff stress. Okay? Right, so all of this, of course, is P internal. Okay? Okay, so that's one work conjugate form. It differs from what we started out here, what we started out with here, by the fact that instead of being over the current configuration, the final expression that we have is about the is on the reference configuration. Okay? And of course, then the integrand just has the notion of stress power, which is defined per unit volume. Right? Okay. So let's press on. And let us do so by going here with, okay, let's work with the last form we have here, okay? Now, let's start here with integral over omega naught, tau contracted with d capital V, okay? And what I'm going to do is to rewrite this using coordinate notation. All right? So I have tau ij d ij. Okay? D capital V. All right? And this I'm going to write now as follows. I'm going to write this now as integral over omega naught tau ij. Now, instead of dij, I'm going to write that as the spatial velocity gradient tensor. Okay? All right? And I want you to think for a few seconds of why that last equality holds. Why am I able to replace the rate of deformation tensor with the spatial velocity gradient tensor? Okay. The reason is because, going into direct notation for brevity, we have that the spatial velocity gradient tensor is its symmetric part plus its skew symmetric part. Okay? But what about the symmetry of tau? Tau is symmetric, right? As a result, when we look at this last expression here, in that contraction, we pick only the symmetric part, and that happens naturally because tau is symmetric, right? As a result, what we've written as the very last integrand is indeed the same as what we have here for this integrand. Okay? So this follows from the fact that tau is symmetric. Okay? So maybe I should add here okay? Those two reasons are what let us get away with that final form. Okay, but then this is also integral over omega naught tau ij. Okay, now vi comma j can be written in terms of f dot I, say capital I, f inverse capital I little j dv. Okay? And what I'm going to do is to take this term and rewrite it as integral over omega naught tau ij, and I'm going to bring that f inverse here. Okay? The reason I can do that, of course, is that when I'm working with coordinate notation, all I have really are just scalars because we're working with the components of each tensor. So we're completely at liberty to move them around, relying upon the fact that multiplication is commutative. The indices take care of everything. Right? The indices and the Einstein summation convention take care of everything else. Okay, I have this. Okay, but now observing the way this contraction works, right, over the little j index, we note that we are also able to rewrite that integrand as tau ij f inverse transpose ji. Okay? F dot ii. All right? And as a final step, I'm going to write this, well, not the final step, but one of the final, we're getting close to the end with this particular manipulation. I'm going to go back to direct notation here. Okay, the reason I have that last expression is because when we look at this, we see that j and j are being contracted out. That leaves a free index little I capital I, but then that is being multiplied out with f dot also little I capital I, right? So there's a contraction of the result of the multiplication of the first two tensors with the third tensor in this expression. Okay, that's what allows me to put a contraction symbol out here. All right. But now, let's also note, that P, which we said was J sigma F inverse transpose, we have that for P, right? This is tau. So we see that P is also tau F inverse transpose. Okay? So, if I just momentarily get back to this slide, look at the very last integral. We have tau F inverse transpose there, right? Which we've just demonstrated is equal to P. So we have this expression. Integral over omega naught P contracted with F dot. Okay? All right. Well, all of this we started with saying that this is all equal to the internal stress power. Okay? So we have yet another expression for the internal stress power, now involving the first Piola Kirchhoff stress and F dot. All right? Okay. All right. Just one more thing now. Let me. So far we have expressions for the internal stress power involving the Cauchy stress, the Kirchhoff stress, and the first Euler-Kirchhoff stress. Okay. So the only one left out is the second Euler-Kirchhoff stress. Let's try to introduce that in the game here. Okay. All right. So continuing. Right, and what I want to do is I want to continue with this last form that we just derived. And in this, I want to introduce our second Euler-Kirchhoff stress. And the way I'm going to do that is to recall from our equations of transformation between these different stress measures that P is also F S. Okay, so we have this contracted with F dot. All right. Again, I'm going to go into coordinate notation to make things clear for us. So I'm going to write this as integral over omega naught, F little I, capital I. Remember, S has indices entirely on the reference configuration, and that product will leave us with free indices little I, capital J, which will be contracted out with F dot little I, capital J, dV. Okay. Now I'm going to invoke the fact that everything here is commutative, so we could write that as S Ij contracted with, okay, how should I do this? I have a couple of ways of doing this. Okay, I'm going to write this as F little I, capital I, F dot little I, capital J, dV. Okay? All right. And then we observe that once again we have a situation. Oh, wait a minute. I actually do not need the contraction symbol here, right? Because I'm working in coordinate notation. Okay? But nevertheless, what I have on the integrand is definitely right. It's just I'm sort of overloading it with notation by putting the contraction symbol there. I don't need it. Okay. So what do we have here? Observe that we have Sij, free indices capital I, capital J, and then when we look at the second sort of grouping in parentheses, we see that that also has free indices capital I, capital J. But then we could also look at this as essentially being F transpose F dot free indices capital I, capital J. Okay? All right. Now, S is symmetric, whereas the quantity in the second parentheses in general is not symmetric. However, the fact that S is symmetric says that, well, because of the properties of contraction, it picks only the symmetric part of what lies in the second parentheses. Okay? So we are actually at liberty to write this thing out, again switching into direct notation. We're at liberty to write this as S contracted with 1/2 of F transpose F dot plus F dot transpose F. What I did here was take this quantity, which is already there, but then add on its transpose, which is here, right? This is just F transpose F dot the whole transpose, right? I added them and took 1/2 of the sum, which is basically writing the symmetric part of either of these, right? should be clear to you that what we have in the final parentheses here is symmetric. Okay, so again, we've done nothing with our expression for the integrand. Right, we're just using the property of one of the many properties of the contraction. Okay, but then I ask you, what can we re-express this entire quantity as? If you recall the fact that, well, I'll tell you what facts to recall, but first let me tell you what it is. It is our Lagrange strain tensor dot. Okay? And the reason for this is because E is equal to 1/2 C minus 1. C is our right Cauchy-Green tensor, which is 1/2 F transpose F minus the isotropic tensor. And sorry, I called that 1 just a second ago, but that's poetic license. Okay. All right. And this then implies that, of course, E dot is 1/2 F transpose F dot plus F dot transpose F. Okay? Because the second order isotropic tensor is a constant, and time differentiating it leaves us with the zero tensor. Okay? And an additional property we've used here is the fact that the transpose and the time derivative are both linear operators, and for that reason they commute. Okay, so it doesn't matter. So the dot of the transpose is the same as the transpose of the dot. Okay, so there's really no ambiguity in what that term means. All right, so essentially we proved it. Okay, so we observe then that for P internal we have many different forms. The form we just derived on the previous slide. Okay, what we have here, right? If I just make that final substitution of E dot for what I've put a brace over, we have P internal has this form involving the second Euler Kirchhoff stress tensor contracted with the time derivative of the Lagrange strain tensor. And because the Lagrange strain tensor is defined entirely on the reference configuration, there's no ambiguity about what we mean by its time derivative. Okay? And just before that, we derived this relation. The first Euler Kirchhoff stress contracted with the rate of the deformation gradient. Okay? Again, no ambiguity because it is defined entirely. Its parametrization is in terms of the reference configuration. Okay? Then moving on to the current configuration, we have two forms again. We have tau contracted with the okay, actually I should be careful about this. I misspoke. This thing is also defined on the reference configuration. Okay? And I need to clean this up because I got ahead of myself here. It's tau contracted with D, the rate of deformation tensor, but integrated over the reference volume. Okay? And finally, we have the expression that we started out with, which is entirely in the current configuration, and that involves the Cauchy stress contracted with the rate of deformation tensor, d little b. Okay? So, we titled this segment Work Conjugate Forms. What we mean by work conjugacy is this idea that each stress tensor acts upon a certain rate of deformation tensor, as in these cases, or upon a certain strain rate, as in this case, or in this case, upon the rate of the deformation gradient. Okay? And all of these give us essentially the same expression for work when integrated over the entire body. Okay? To note, of course, is that the integrands are defined over different configurations. This is the first three, in fact, are defined over the reference configuration. So if we take just those integrands, they would give us the corresponding stress powers per unit volume in the corresponding configuration. Okay, so this is an important idea to really understand how these stress tensors act upon deformation, where they really live, and how they act to affect thermodynamics and rate of energy change and all that. Okay, we'll be using these again as we move on through the course. Okay, we'll stop here.